Question 21 from the National 5 Physics Examination from the SQA, and this is section 1. The diagram represents a wave, and we're asked to find which row in the table shows the wavelength and the amplitude of the wave. Well, let's see how many wavelengths fit in between this distance here, which is 120 millimeters. Remember, a wavelength is a complete up and a complete down of the wave. So there we have a complete up and a complete down, so that's one wavelength. And there's a second wavelength, a complete up and a complete down. And there's a third wavelength, a complete up and a complete down. So we have three whole wavelengths covering a distance of 120 millimeters. So that must mean one wavelength is 120 divided by 3 millimeters, and therefore one wavelength is going to be equal to 40 millimeters. So we've got a choice between C and B. Now what about the amplitude? Well, the amplitude is really half the distance from the peak to the trough. There's the amplitude in here, that's that part in there. And we can see from the peak to the trough is 0.2 meters. So therefore the amplitude is going to be 0.1 meters. So the amplitude is going to be equal to 0.1 of a meter. So we're looking for a response of 40 millimeters and 0.1 meters. And it's got to be a response of B, because the wavelength is 40 millimeters and the amplitude is 0.1 meters. And our response is going to be B. Question 22. A teacher gives a group of students 2 clues to identify a particular band of electromagnetic spectrum. The first clue is it diffracts around obstacles more than visible light. And the second clue is it has a greater frequency than microwave radiation. Well, let's look at the first clue. It diffracts around obstacles more than visible light. Well, if you remember our diffraction patterns for different wavelengths, you can see that wavelengths with a longer wavelength are better at diffracting around objects. Short wavelengths are not very good at diffracting around objects. So this wave we're looking at, this clue, tells us that the wavelength is going to be bigger than visible light. Now let's take a look at the spectrum chart and we can help ourselves here as well. So we've got the following to deal with. We have that the wavelength is going to be bigger than visible light, because it's going to diffract better than visible light. So it's either got to be infrared or microwaves or radio waves. So the second clue should help us. The second clue is it has a greater frequency than microwave radiation. So microwave radiation is here. A greater frequency must be this one here. So it looks like our response is going to be infrared radiation. It's got a bigger frequency than visible light. It's got a bigger frequency than microwaves. It's got a smaller frequency than visible light, and it satisfies also clue number 1, which says it's going to diffract better than visible light, which means it must have a bigger wavelength than visible light, and it has. So therefore, our response for this question has got to be B. Question 23. A radioactive source has an average activity of 5.2 megabecquerels over a time of 1.2 hours. The number of nuclear disintegrations that occur in the source in this time, and we're given the 5 responses. When we look up a relationship sheet, we know that the activity of a source measured in becquerels is the number of disintegrations divided by the time. So if we rearrange that to give us the number of disintegrations, it's equal to the activity times the time in seconds. And what is the activity? It's 5.2 megabecquerels, so be careful, it's going to be 5.2 times 10 to the power 6 becquerels. And we've got to multiply this by 1.2 hours, so 1.2 hours is times 60 times 60, and that's going to give us seconds for this one. So we do that with a calculator, we end up with a number of disintegrations to be 2.2 times 10 to the power 10 disintegrations. And that's going to give us the following response, response E. Question 24. A sample of tissue is exposed to a source of alpha particles. The equivalent dose received from this source during a time of 5 minutes is 480 microsieverts. And we've got to find the equivalent dose rate. Well, if you look up your relationship sheet, we have the equivalent dose rate is H dot, and that's equal to the equivalent dose divided by the time it was received. So it's going to be equal to the following. It's going to be 480, and we have to put in microsieverts, I'm going to divide by 5 minutes, which we know we've got to change into 5 times 60. That's going to give us seconds here like that. So 480 microsieverts divided by 5 times 60 is going to give us an answer of 1.6 microsieverts, and remember that seconds, so it's seconds to minus 1. So our response is 1.6 microsieverts per second. That's going to be response A. Question 25, the final question in paper 1 of the 2025 National 5 Physics exam. Energy is released when two small nuclei combine during a nuclear reaction to form a larger nucleus. So what have we got? We've got two small nuclei combining like this to give us a bigger nucleus, and of course we're going to have some energy released here. Now when you get two small nuclei combining together, that is going to be fusion, nuclear fusion when that happens. Fusion means a joining together. So our answer, our response for the final question is going to be nuclear fusion, which is response B.